Ever wondered why airlines basically turned their backs on the Airbus A380, yet they are still lining up for the Boeing 777X, even though it is nearly 7 years late? Now, I'm not talking about the usual "it's too big" argument. I'm talking about the hidden specs. For instance, did you know the A380 would be 15% more fuel efficient today if Airbus hadn't gambled on versions that were never ever built? There is a lot of engineering drama behind these two jets that rarely makes the headlines. You will want to see this. And hey, if you find this breakdown interesting, hit the subscribe button. It really helps a small creator like me to keep digging into these stories. Let's get into it. Infrastructure integration and geometric constraints. Firstly, let's start with those fancy wingtips on the 777 and look at what they really give to the airlines. The most significant operational hurdle for ultra-large aircraft is their interaction with existing airport geometry. The Airbus A380 was famously designed to fit within an 80-meter by 80-meter box, a constraint that dictated every major aerodynamic decision. The A380-800 is a permanent ICAO Code F Group 6 aircraft. This designation requires airports to provide runways with a minimum width of 60 meters and taxiways with a minimum width of 23 meters, along with significantly increased separation between parallel taxiways and runways to prevent wingtip collisions. The global adoption of the A380 necessitated billions of dollars in infrastructure upgrades, from strengthening bridges to installing specialized dual-level jet bridges. These costs acted as a massive entry barrier, effectively limiting the A380 to approximately 60 to 80 major global hubs. The Boeing 777-9 approaches this problem with a geometric dual identity. During flight, the wingtips are extended to a span of 71.8 meters, placing it in the same Code F category as the A380 for airside operations such as takeoff and landing. So what I mean? The 777X also require runways with a minimum width of 60 meters. However, upon exiting the runway, the outer 3.5 meters of each wing fold vertically, reducing the wingspan to 64.8 meters. This allows the 777-9 to operate as a Code E Group 5 aircraft on the ground, envelopes as the Boeing 777-300ER and Airbus A350-1000. The 777-9 is notably longer than the A380, making it the longest passenger airliner ever produced. This length presents its own challenges for gate depths, but the folding wingtips eliminate the need for the lateral space expansions that the A380 demanded. Maneuverability and ground operations. The hidden complexity of ground maneuvering lies in the minimum turning radius and the 180-degree turn capability. The A380, despite its mass, achieves a surprisingly tight turn width of 50.91 meters, but only through the use of differential braking and asymmetric thrust, techniques that increase the tire wear and engine stress. The 777-9 requires a wider 59-meter pavement width for a standard U-turn without differential braking. A critical deal breaker for the A380 in ground operations is its turnaround time. Due to its double-deck configuration, the A380 requires specialized catering trucks and cleaning crews that can access both levels simultaneously. A typical long-haul turnaround of an A380 takes approximately 180 to 210 minutes, whereas the 777-9 is targeted to achieve turnarounds in 90 to 120 minutes, significantly improving aircraft utilization rates. Aerodynamic architecture and wing physics. The divergent philosophies of Airbus and Boeing are most apparent in the wing design. The A380 wing was over-engineered for a larger -900 stretched variant that was never built, resulting in a wing area that is excessively large for the current -800 model. Aspect ratio and induced drag penalties. The aspect ratio, AR, of a wing is defined as the square of the wingspan, B, divided by the wing area, S. For the A380, the AR is approximately 7.5 to 7.8, which is significantly lower than the 9.0 to 9.5 found on the newer twin jets like the 787 and A350. This low aspect ratio is a direct consequence of the 80-meter wingspan limit. To provide enough lift for a 575-ton aircraft within that span, engineers had to increase the wing chord, leading to a massive wing area of 845 meters squared. The aerodynamic penalty is severe. Induced drag due to weight, accounts for a 50% of total drag at cruise, which is 10% higher than it would be with an optimal 90-meter wingspan. The 777-9, by utilizing carbon fiber reinforced polymers CFRP and folding wingtips, achieves an aspect ratio of approximately 11.04. This slender wing generates lift much more efficiently and allowing for a higher cruise speed of Mach 85 compared to the A380's economical Mach 83. Wing loading and thrust-to-weight ratios. Wing loading, W divided by S, is a critical metric for takeoff performance and cruise efficiency. The A380 has a relatively low wing loading at MTOW due to its oversized wing, while the 777-9 operates at much higher pressures. The higher thrust-to-weight ratio of the 777-9, powered by the massive G9X engines, allows for superior climb gradients and better performance in hot and high conditions. The A380, while powerful, is hampered by its massive empty weight, which is nearly 10,000 kilograms heavier than the 777-9. Propulsion systems, G9X versus the quad-engine paradigm. The propulsion system is perhaps the single most important deal-breaker in the comparison. The A380 utilizes 4 engines, from either the Engine Alliance GP7200 or Rolls-Royce Trent 900. These engines represent late 1990s technology, which was quickly eclipsed by the G9X and Trent XWB generations. Thermodynamic efficiency and the GE9X. The G9X is the largest and most powerful commercial engine ever built, featuring a 134-inch fan and 27:1 compressor pressure ratio. It offers a 10% reduction in specific fuel consumption, SFC, compared to the G90-115B, and a nearly 20–25% improvement over the engines powering the A380. One hidden specification is the engine weight fraction. On the 777-9, the 2 G9X engines represent a smaller percentage of the MTOW than the 4 engines on the A380, despite the G9X's massive size. This is because the twin-engine configuration eliminates the need for 2 extra pylons, dual fuel lines, and complex quad-engine synchronization systems, engine maintenance cycles, and durability issues. A significant deal-breaker for the A380 is the sheer cost of engine maintenance. With 4 engines, an airline faces twice as many shop visits as a twin-engine operator. Engine maintenance for an A380 can reach $30,000 per flight hour, whereas a 777 operator typically spends $7,000 to $9,000 per hour on a 300ER, with the 777-9 expected to be slightly higher due to the complexity of the G9X. However, the G9X has faced its own challenges. In early 2026, a durability issue was identified regarding a seal in the high-pressure compressor. This issue led to a temporary flight test slowdown, with only 2 of 5 test aircraft flying in February 2026. While Boeing maintains this will not delay the first delivery in 2027, the long-term reliability of these ultra-high-pressure engines remains a concern for launch customers like Emirates and Lufthansa. Pavement dynamics, ACN, ACR, and CDF analysis. A hidden specification critical to airport planning is the impact of the aircraft's weight on the physical life of the runway. This is measured through the aircraft classification number, ACN, or the newer Aircraft Classification Rating, ACR, the pavement-friendly giant. Despite its 575-ton mass, the A380 is famously pavement-friendly. This is due to its 22-wheel landing gear configuration, which distributes the weight more broadly than the 14 wheels on the 777-9. The A380's main landing gear, MLG, consists of 2 6-wheel body gears and 2 4-wheel wing gears. The cumulative damage factor, CDF, analysis shows that the A380's wide gear track, 12.5 meters between wing gear axles, places the heaviest loads on the sections of the runway that are rarely used by other wide-body aircraft. Standard long-range jets, like the 777-300ER, have tracks between 10.6 and 11.9 meters. Consequently, the A380 contributes roughly 30% less to the peak pavement damage of a typical fleet mix than its gross weight would suggest. 777-9 pavement stress and ACR values. The Boeing 777-9, by constant, concentrates its 352-ton taxi weight onto 2 6-wheel trucks. To support this weight, the 777-9 uses higher tire pressures, 229 psi, than the A380, 218 psi. Higher tire pressure leads to higher vertical strain in the upper layers of the asphalt, potentially accelerating pavement cracking. The deal breaker here for small airports is that while the 777-9 fits in the gate, it may require runway strengthening if the subgrade is ultra-low, category D, as its ACR exceeds the PCN of many secondary airports. Cabin environment and psychoacoustics. Passenger experience is often marketed through luxury, but the true differentiators are noise levels, cabin altitude, and humidity, factors that directly influence jet lag and fatigue. The A380 noise advantage. The A380 remains the quietest large aircraft ever built. Measurements show that at cruise, the A380 mid-cabin noise level is approximately 68 dB, compared to 73 dB of the 777-300ER and roughly 70 to 71 dB for the 787 and A350. Because the decibel scale is logarithmic, a 5 dB difference represents a nearly 300% difference in sound intensity and 25 to 30% difference in perceived loudness. The A380's noise profile is also flatter, lacking the high-frequency hiss of airflow found in twin jets. This makes it the perfect aircraft for ultra-long-haul premium travelers. 777X atmospheric improvements. The 777X counters the A380's quietness with superior cabin atmosphere. By utilizing the 787's environmental control systems, the 777-9 maintains a cabin altitude of 6,000 feet, even at a flight level of 41,000 feet. The A380, designed with older aluminum alloys, typically maintains a cabin altitude of 7,000 to 8,000 feet. The 777X also features higher humidity levels and advanced filtration, which reduces the dry eye and dehydration symptoms common on the A380. Economic deal breakers. The cargo revenue gap. The most profound hidden specification that led to A380's commercial failure is the cargo-to-passenger ratio. Airlines generate a significant portion of their profit from belly cargo, which subsidizes the cost of the passenger flight. The A380 is a volume-limited aircraft. Its double-deck configuration uses up almost all the internal fuselage volume for passengers, leaving very little space for freight. The A380 provides approximately 133 cubic meters of cargo space, while the 777-9 provides a massive 230 cubic meters. On a route like Dubai to New York, JFK, an A380 burns roughly 65 tons more fuel than the 777. To carry potentially only 100 extra passengers, this makes the A380 economically unviable on any route where it cannot maintain a passenger load factor of at least 85%. The 777-9, with its high cargo capacity, can remain profitable even with a 60% passenger load, because the belly freight covers the fuel bill. The A380neo engineering realities and failure. The A380neo new engine option was a proposed upgrade meant to bridge the efficiency gap between the A380 and the 777X. However, the project was never launched due to a series of technical and financial death spirals. To achieve a 10 to 15% fuel burn reduction, the A380 requires modern engines like the Rolls-Royce Trent XWB or a D-rated GE9X. These engines have significantly larger fan diameters, 118 to 134 inches, than the original Trent 900, 116 inches. The heavier engines would increase the bending moment of the wing, requiring hundreds of kilograms of structural reinforcement. To maintain ground clearance for the larger nacelles, the landing gear would need to be lengthened, adding even more weight. Larger nacelles increase the wetted area and form drag, which would negate about 2 to 3% of the engine's efficiency gains. Airbus calculated that the OEW, operating empty weight, increase would be so significant that the NEO would only offer a 5 to 10% net improvement in fuel burn, not enough to justify the $3 billion development cost. Engine manufacturers like Rolls-Royce were unwilling to invest in a backspoke engine for the A380 when the total remaining order book was so small. Unlike the A320neo, which had thousands of orders, the A380 was a one-customer aircraft, Emirates. Developing an engine for a fleet of only 100, maybe 200 aircraft was commercially impossible for the OEMs, especially when they could focus on the A350 and 787 markets where thousands of engines would be sold. System architectures and hidden specs. Beyond the airframe and engines, The internal systems of this aircraft represent two different eras of electrical and hydraulics engineering. Hydraulic pressure 5000 psi versus 3000 psi. The A380 was the first commercial aircraft to utilize a 5000 psi, 35 megapascal hydraulic system, a significant jump for the industry standard 3000 psi. High-pressure hydraulics allowed Airbus to use smaller, lighter actuators and thinner titanium piping to move the massive flight control surfaces. This saved approximately 1000 kg in weight. The 777X maintains a hybrid approach, but relies more on electromechanical actuators for secondary systems, reducing the reliance on heavy hydraulic fluid lines throughout the cabin. Electrical generation. Variable frequency versus constant speed. The A380 utilizes 450 kilowatt variable frequency generators. By allowing the generator frequency to vary with engine RPM, Airbus eliminated the heavy and maintenance-intensive constant speed drive (CSD) found on older jets. The 777X takes this further, utilizing a 787-style, more electric architecture, where the auxiliary power unit (APU) and main engines provide massive electrical reserves to power the environmental control systems (ECS) without the need for traditional bleed air from the engines. This no-bleed or low-bleed approach improves engine efficiency by 2–3% by not siphoning off high-pressure air from the cabin. Operational resilience, fact check and 2026 outlook. As of February 2026, the status of both programs has been affected by the global recovery and technical setbacks. The 777X program is currently 6 years behind its original schedule, with the first delivery to Lufthansa now expected in second quarter of 2027. The FAA and EASA have increased their oversight, requiring a phased type inspection authorization that has slowed progress. Despite this, the order book has remained resilient, with Emirates adding 65 more 777X units at the Dubai Air Show 2025, bringing their total commitment to 270 aircraft. The A380 has defined early retirement predictions. As of April 2024, there were 189 aircraft in service with 10 operators. By 2026, the global fleet valuation has increased by 2.8%, as airlines realize they cannot meet post-pandemic demand without the super jumbo's capacity. Emirates plans to fly the A380 until 2040, investing in massive cabin refurbishments to keep the fleet modern while waiting for the 777X. Maintenance and life cycle costs. Maintenance costs are the ultimate hidden spec that determines the long-term viability of an airframe. The deal breaker for many A380 operators like Air France and Thai Airways was the sunk cost of point-to-point operations. By the time an A380 is turned around and ready to fly, the airline has already spent nearly $500,000 in fuel, staff and landing fees. On a twin jet, these fixed costs are significantly lower, providing the airline with more exit liquidity if a route underperforms. Now share your thoughts in the comments. Maybe you know more interesting hidden specs. I'll be really interested to hear your opinion. Don't forget to like and subscribe. But now let's meet in some of these videos. See you!